Now we will go through the third type of classification of colloidal solutions, and this classification is based on the type of the particles of the dispersed phase, right? We know that colloidal solution has two phases: dispersion medium, right, which is same as solvent in case of true solutions, and dispersed phase, which is same as solute as in true solutions, right? So now we will see the different types of dispersed phases, right, based on which this classification will go, right? So this classification is based on types of particles in dispersed phase, right? So based on this classification, we have three types of colloidal solutions. First is micromolecular colloidal solutions. I'm sorry, not micromolecular, I'm sorry, it's multimolecular colloidal solutions. The second is macromolecular, and the third is associated colloids, which are also known as micelles, right? So let's write down here. Then we'll also compare the three. The first is your multimolecular, right, colloids. Second is your macromolecular colloid, and the third is your associated colloid, also known as micelles, right? If you look at the first type of colloidal solution, it says multimolecular. Multimolecular means something made up of multiple molecules, right? More than one molecule, right? So in this type of colloidal solutions, the colloid or the dispersed phase is made up of number of molecules or atoms, right? So here, just simply look at the word, you will get to know what it is actually. Multimolecular means multiple molecules are there in the dispersed phase particles of multimolecular colloid, right? So here the dispersed phase will consist of multiple molecules or atoms, right? So in solution, multiple atoms or molecules, right, will associate, right, to form particles of colloidal range, right? So here, if these are some atoms or molecules, right, they will associate like this. All these atoms will associate or aggregate to form this type of particle, right? This is your colloid, right? And the size of each particle in this case, right, that are aggregating to form colloidal size particles is less than 1 nanometer, right? Here the size of particles that are associating is less than 1 nanometer. And if you remember, these come under the category of true solutions, right? So the solutions in which the particles are less than 1 nanometer, they are known as true solutions, right? So particles whose size or the diameter is less than 1 nanometer will associate to form colloids whose size would be between 10 to the power of, if you take it in nanometer, it would be between 1 nanometer to 1000 nanometer. Right? So these particles, when number of particles having size 1 nanometer will associate to form a bigger particle of this range between 1 nanometer and 1000 nanometer, we get a multimolecular colloids, right? An example of these type of colloids are gold sol and your sulfur sol. Gold sol, that means gold sol, when we talk about gold sol, it means that colloidal solution of gold is formed from number of or multiple or more than one atoms of gold, right? So multiple gold atoms will associate, right, to form particles of colloidal size, right, in case of gold sol. Similarly, if you look at, so here atoms associate, right, in case of gold sol. Similarly, in case of sulfur sol is formed when multiple sulfur molecules, acid rings of sulfur molecules, will come close together and associate to form particles of colloidal size, right? So here sulfur molecules which are acid rings will associate, right? And when these atoms or molecules associate, like here, right, the particles in this associated colloid are held together by weak van der Waals forces, right? So here I'll mention particles are held together by weak van der Waals forces of attraction. Right? So this is your second point. Right? Now let's talk about macromolecular colloids. Macromolecule means big molecules, right? So colloidal solutions that are called as macromolecular colloid consist of bigger molecules, right? Bigger molecules, example, your proteins, enzymes, right, or polymers like polyethylene, nylon, rubber, all these are bigger molecules, right? These types of molecules you have studied in organic chemistry in chapter biomolecules and polymers, right? So here macromolecule means bigger size molecules. When they are dissolved in a suitable solvent, right, they will form colloidal solutions, right? So dispersed phase of these macromolecules will consist of particles of colloidal size, which is in the range of 1 nanometer to 1000 nanometer, right? So these are formed from big molecules. Big molecules are polymers, right? So if we talk about the starch, cellulose, right, proteins, we know proteins are big molecules that are made up from amino acids, right? Similarly, enzymes are also proteins, right? These are natural polymers, and there are some man-made polymers like polyethylene, right, nylon, rubber. All these big molecules or macromolecules, when dissolved in a suitable liquid, they will form particles of, or they will form dispersed phase, right, which consist of particles of this range, 1 nanometer to 1000 nanometer, right? So since these molecules are big, right, so their molecular mass will also be high, right? So the molecular masses are high. Since these are big molecules, their molecular masses are high, right? And these are held together, right, by van der Waals forces of attraction, which are stronger as compared to van der Waals forces acting in multimolecular colloids, right? So here, this is first, this is second. Here particles of macromolecules, particles are held together via strong van der Waals forces, right? Why strong? Because these molecules are big, right? They consist of long chains, right, big molecules. So force of attraction, van der Waals force of attraction, is high compared to multimolecular colloids. And we said since these are big molecules, so their molecular masses would also be high. Molecular masses are high, right? And in this case, molecular mass is low, right? So these are formed from multiple molecules and atoms, and these are formed from big molecules. Let's come to the third type of colloid, which is your associated colloids. Associated colloids, as the word says, associate, right? So particles that associate in this type of colloid are ions, right? So when in solution, right, ions aggregate or they associate, right, they form bigger particles of colloidal size, right? So these are known as associated colloids. If you look at this, these are also formed from association of smaller particles, right? And these are also formed from association of smaller particles. The difference is multimolecular colloids are formed from atoms and molecules, but these are formed from multiple ions, right? So these are formed from ions, right? These are formed from ions, and we'll just look into little detail of what are associated colloids, right? Associated colloids, we would be doing a different video lecture that will in that video lecture we will discuss in detail what exactly is associated colloid and how these are formed, right? So these are formed from ions, or better, these are formed from aggregation of ions, right? How these are formed, let's just talk a little about this. The example of most common example of associated colloids are soaps, right? So soaps, when dissolved in water, they will form associated colloids known as micelles, right? And these types of colloidal solutions are formed at little higher concentration, right? What do we mean by that is, if soap is dissolved in water, right, at low concentration, soap will act as strong electrolytes, normal strong electrolytes, right, like that of true solutions. But when you increase the concentration of soap in water, right, it will start associating, right? The particles of soap will start associating to form associated colloids or micelles, right? The soaps, what are soaps? Soaps are sodium salts of higher fatty acids. Higher fatty acids are carboxylic acids only. So when you treat higher fatty acids with sodium hydroxide, they will form soaps, right? An example is stearic acid and palmitic acid, which are higher fatty acids. They will form sodium salts with sodium hydroxide. So sodium salt of stearic acid and palmitic acid, which is sodium stearate or sodium palmitate, are your soaps, right? So let's take example of sodium stearate, CH3 CH2 16 COONA, right? This is the formula of sodium stearate, which is a soap, right? So when you dissolve it in water, it will dissociate to form CH3CH2 whole 16 COO negative ion plus sodium ion, right? Now at low concentration, right, at low concentration, this soap, right, will behave like strong electrolyte, right? Normal, this will behave like strong electrolyte, right? So but when you increase the concentration of sodium stearate, which is a soap, in water, then at higher concentration, these ions, these are your stearate ions, these stearate ions will start interacting or will start aggregating, right, to form bigger particles, right, to form bigger particles of colloidal range, right. So at high concentration, the stearate ions, stearate ions will start aggregating to form associated colloids, which are known as micelles, right, associated colloids known as micelles, right. Since we said that this takes place at high concentration, so the concentration above which this micelle formation takes place from these stearate ions, that concentration is known as critical micelle concentration, right. So this high concentration this takes place above CMC, right, because we said this micelle formation doesn't takes place at low concentration, because at low concentration it's behaving like a strong electrolyte, but at higher concentration these ions are aggregating, right, or at higher concentration ions will start aggregating to form ionic micelles, right. So the concentration above which these ions will start aggregating to form ionic micelles, that concentration is known as critical micelle concentration, CMC, right, and this takes place above a certain temperature. That temperature is known as Kraft temperature, right, takes place above CMC, critical micelle concentration, and above Kraft temperature, which is TK, denoted by TK, right. So this is it. In this video lecture we will look into detail the formation of ionic micelle in another after this video lecture, right. So these are formed from aggregation of ions. Now we know how it gets formed, right. An example is your soaps and detergents also, right. So these are held together by van der Waals forces, same as these two colloids. Associated colloids are also held together, that is ions in associated colloids are held together via van der Waals forces, and the van der Waals forces depends on the strength of van der Waals forces will depend on the concentration of solution. Higher is the concentration, higher would be the van der Waals forces of attraction, right. So here we will mention ions are held together via van der Waals forces that depends on the concentration of ions, right. Ions are held together via van der Waals forces that depends on the concentration of solution, right. Higher is the concentration, more would be the ions, so more ions means one van der Waals forces would be high. And what about its molecular mass? Molecular mass, if you look at this molecule, this molecule is quite big, right, compared to sodium or this sulfur, right. These molecules are bigger, right. Even if you look at glucose or cellulose or your proteins, right, these molecules are quite big, so their molecular mass would be quite high, right. So here molecular mass is quite high, right. This is it. So just go through this. Just remember the type of particles, right, that are associating to form colloidal solution. Here ions and molecules, here big molecules, here ions, right. And look at all these are held together by van der Waals forces of attraction. Here molecules are big, so van der Waals forces of attraction is high. Here the van der Waals forces of attraction increases with increasing concentration, and here since the atoms and molecules are small, so van der Waals forces of attraction is low, right. And molecular mass, since these are small atoms or molecules, molecular masses is low, Here the molecules are big, so molecular masses are high. Here in case of associated colloids, molecular masses is quite high. It's not too low, too high, it's little high on higher side, because if you look at the molecules, these are higher fatty acids, right? So the molecular masses are quite high. I hope all this is clear to you. Thanks.